Now, it is a very common experience that when we apply force to certain objects, they become deformed. Okay, so here is a rubber band, very common rubber band that I'm sure you all must have seen. Now, in your experience, if you would apply force to this rubber band, you would deform it, you would change its shape. Okay, so this deformation, the process of this deformation, when it is done systematically for engineering purposes, we arrive at something which is known as stress-strain curve. Okay, it is nothing but when we apply certain force in a certain way to the objects, then they become deformed, they experience strain. Okay, so that is what this curve is trying to capture. So look at this video right here. Here we have a steel bar. Now this steel bar, what I am trying to do is that I am applying force to it. I am pulling it from both ends and it is undergoing deformation. Okay, its length is slowly and gradually it is increasing. So okay, look at this again. Okay, so its length is increasing until at a certain point it develops a neck. Okay, it becomes completely deformed, it becomes thin from here, it develops a neck, and then finally it breaks. Okay, so that process that what we saw in this video is captured by something known as stress-strain curve. Okay, so this is the stress-strain curve of very common ductile materials. Okay, so ductile materials, the example for ductile materials would be the metal bar that we have just shown, right? Metals such as aluminium, steel, okay, iron, those kinds of materials are ductile materials. Okay, and the metals are good examples. Okay, and this is the example of how they experience strain within them, inside them, how they experience strain, how they become deformed when forces are applied to it. And this is the diagram again which we are representing, that process that we just saw in the video, we are representing using this diagram. So here in this metal bar, I am applying a force to this metal bar, and because of this force, the metal bar is actually expanding, its length is changing. This change in length divided by the original length is a measure of strain. Okay, so that would be our measure of strain. Okay, so there are several measures of strain. For our purposes, we'll keep things simple, and our measure of strain, whenever we talk about, this is the picture which should come to your mind, and strain is actually L by delta L, which is the change in length divided by the original length L, and that is the strain. It is just proportional, it is just the ratio of two quantities, it is unitless, if you will. And stress is the force that has been applied per unit area of this bar. Okay, so for our purposes, that is the stress. What is the stress? The stress is the force F. Here F is equal to mg, of course. Okay, so we will just divide it by the area, the cross section area. Okay, and that, of course, for our diagram, that would be the mg by area. So with that basic understanding, let us now understand how the materials, how they behave. Okay, so this is the curve that we would get. So the stress, we are slowly and gradually we are increasing the stress, we are applying more and more, pulling this bar harder and harder, and because of which there is a change in the delta L, and that would be the measure of our strain. So initially, when we start increasing the stress, we will see that the strain, it increases linearly. So this is the linear increase, and here this is the elastic behavior. The change is proportional, the stress is proportional to the strain, and this is the Hooke's law, right? What is Hooke's law? Hooke's law says that the strain is actually proportional to the stress, or in other words, if I were to divide these two, which means if I do stress by strain, then this comes out to be a constant. We denote it by a symbol Y, and this is known as Young's modulus. Okay, so this is the stress-state relationship, the very beginning OA portion. This is the also known as proportional limit, this OA portion. Here it exhibits perfectly elastic behavior where the stress and strain, they are linearly related, they are proportional to each other. This is known as proportion, or also the Hooke's region. Okay, so this is the Hooke's region. After this, what happens is that as I increase the stress furthermore, the strain does not change that much. Okay, the strain does not change that much. it is still changing, but the slowly and gradually the change in strain actually decreases, and I reach the point B. So this point B is known as the elastic limit, okay. So the material is still elastic, okay, even in this region the material is elastic, but at point B I have reached the elastic limit. This is the elastic limit, that is what I have reached at the point B. Now from here, if I release the material, if I see between A and B, the material is still elastic, but it is not directly proportional, okay. So in the region of proportionality, this is the Hooke's region, okay. This is the Hooke's region where the Hooke's law applies, where the stress is proportional. Between A and B, the material is still elastic. What does that mean? It means that if I release the stress, I will go back to the original position, okay. Even this will happen even till point B. If I release, then I still go back here. After point B, if I continue to increase the stress, then there is some permanent damage started happening because the strain is not increasing. What does that mean? It means that the bonds inside the material are actually they have started breaking. Okay, so after this, if I continue to increase the stress, the strain actually decreases, which means that the material, its strain is decreasing because the energy is now being used to actually break the bonds. So between B and C, this is what is happening, and if I continue to apply the stress after point B, then the deformation starts becoming permanent. So after point B, we say this region is plastic region. What does it mean, plastic region? It means that I am making the material permanently deformed. So after this, the material becomes permanently deformed, and now if I release the forces, then the material would go back, but not to its original position. It would go to its new position. Okay, there would be a completely new position, which would be point which would be formed in the stress and strain relationship, and even after the stress is gone, the material would remain slightly strained. Okay, that is what this means, because the bonds, I have done some permanent damage. After point B, I am starting doing some permanent damage to the bonds of to the structure of the material. That is why it cannot go back to the point O. It will go back to a new point O dash. Okay, even between this point O dash and B dash, the Hooke's law is obeyed. Okay, notice that those two lines are actually parallel. These two curves, OB and O dash B dash, these are actually parallel. So between O dash and A dash, the Hooke's law would still be obeyed. Stress-strain relationship, the Young's modulus would still remain the same. It is just that even after I have removed the stress completely, the material, because it is permanently damaged, there would be some strain which would be present inside the material. Now, after that, after point B is the point where this is the maximum stress which could be borne by the material. That is the maximum stress which could be borne by the material without actually showing the plastic behavior. Okay, so that is the B is that point. This is the maximum stress point. It is known as upper yield point. Okay, so that is the maximum stress which is required to initiate the plastic behavior of the material. The point C is known as minimum yield point. So point B is maximum yield point C is the minimum yield point, and this is the minimum force or the minimum stress required to exhibit the plastic behavior. So at point B is the maximum, this is the elastic limit also. Point B is known as elastic limit or the maximum yield point, upper yield point. And what does that mean? It means that it is the maximum stress which is required to show the plastic behavior of the material, and point C is the minimum yield point or the lower yield point, and this is the minimum stress which is required to exhibit the plastic behavior. In some ways, this is the maxima and minima basically in the initiation, in the beginning of the plastic region, this entire region from here on till point D, this is known as plastic region. Okay, so we'll just color it differently. From here, point B till point D, this is known as plastic region. Why? Because some permanent damage. If I am applying to stress in this region, if I have taken the material to this region, then there is some permanent damage which I am causing to the material, and I am changing the structure of the material, and this will exhibit itself as plastic deformation. Plastic deformation is that deformation which cannot revert back to its original condition. In the beginning, there is a maxima and minima in this plastic region, and those are known as the upper yield point and the lower yield point. Between C and D, the material continues to exhibit the plastic behavior. Plastic behavior means that as I am deforming the material, as I am applying a stress to the material, it will become permanently deformed. At the point D, the material starts exhibiting the necking, right? There is a neck formed. So like we saw in the video beginning, this is the point where the material starts breaking in some sense. Material starts failing. So there will be a small neck formed, and finally at point E, that is the fracture would happen. Beyond point D, so point D is actually the maximum stress point. Okay. This is the point. If I take the material is able to handle maximum stress at this point D. If the material has already developed neck, then it cannot really it will handle the stress only less than D, and it will fracture. Okay, even at the stress less than D, it would fracture if it already developed the necking. So D, in some sense, is the ultimate stress point. That is the maximum stress which could be borne by the material before it starts necking and it starts breaking, it starts failing. And then between D and E, the necking happens, and at the point E, the fracture would happen. So this is the stress strain curve for ductile materials. Now that is again very important thing here, that this is only applicable to ductile. Ductile materials are those materials which actually show the ductility. Okay, they are able to withstand the stress in some sense. They have some kind of elastic behavior, like the steels, the metals. Okay, so now in this region where our Hooke's law applies, we have a very special behavior of material wherein we can apply the stress to the material and it would develop the strain. When we remove the stress, then the material will give back the same amount of energy and return back to the original position. After point B, this does not really happen. After point B, some amount of applied energy becomes permanently stored inside the material. And why is that? Because the bonds, I have permanently broken them. They cannot join together. Okay. So after point B, because I have broken the bonds, if I apply stress beyond point B, then the material, that amount of work that I have done, I would never be able to get back, because that work is permanently stored as potential energy inside the material. And after that, even if I remove the stress, the material would now go back backwards to a new point where there is some permanent strain present, some potential energy is permanently stored inside the material. So even between point O and B, this region O and A, where there is a linear relationship, where the Hooke's law applies, is the most important. In the case of our simple bar example, this region, the constant of proportionality between the stress and strain, okay, so stress divided by strain in this region is known as Young's modulus. Okay, so this is the Young's modulus that we understand, okay, that we know. So what is modulus of elasticity? So modulus of elasticity are the various ways of calculating the stress and strain. In the case of rods, in the case of single dimension, when we are computing it only in the case of L and delta L, like we saw here in this figure, okay, only in this case, the modulus that we are computing, the modulus of elasticity that we are computing is actually the Young's modulus. But in this region, I can compute the modulus, the elasticity behavior, the various modulus. Okay, I can compute, for example, the volumetric. I can just say that I have taken a ball of steel and I am compressing it from all sides, and in that way, I can compute the stress and strain, and that would be another kind of modulus of elasticity. So, in some sense, Young's modulus is one type of modulus of elasticity which helps us understand the behavior of the material in this region, the elastic behavior, where the stress and strain are linearly related. Okay, there are other kinds of modulus of elasticity as well, and those are known as bulk modulus, shear modulus, other kinds of modulus as well. But for our purposes, if we understand the Young's modulus, which applies to the where we are measuring the stress and strain in terms of length, okay, and the axial, basically the axial component of the stress we are measuring and the strain we are measuring in terms of change in length, that Young's modulus, for our purposes, that particular modulus of elasticity would actually suffice. Okay, so hopefully the stress strain curve is very clear. We will be taking several classes on this, various versions we will be studying for this, various terminology we will be studying using this stress strain curve. So definitely subscribe to the channel, and then finally eventually we will be deriving a formula for the Young's modulus, and we will be doing some numericals. Thank you.